morning. This is Dr. S.P. Harsa from Mechanical and Industrial Department, IIT Roorkee. I am going to deliver today lecture 9 on the subject of the strength of materials, which is developed under the program of the National Program on National Technological Enhanced Learning. If just I want to refresh those things, like in previous lectures we had discussed about that what the strain is, what the basic concept of the strains. When you apply the load, there is a deformation, and if you want to measure the deformation, there is a technical term known as the strain. And then also we defined that actually if we apply the load, a kind of deformation which we discussed, if it is under the elastic one, means if you remove the load and body comes to its original state, then what the laws are there, then we establish the relation between the stresses and the strain within the elastic deformation, that is based on the Hooke's law. And then based on the Hooke's law, we also defined one of the elastic constant, that is the Young's modulus of elasticity, and you see it is defined for the proportionality between the stress and strains. And once we apply the load, you see in the uniaxial directions like in x, y or z direction, there is a impact is there on other directions, like you see the y or z. So to measure the deformation in other directions, we want to compute that actually what the the relation is there in between. You see when you apply the load in x direction, there is a contraction is there. Let us say if the tensile load is there, an extension is there in the x direction, then there is a contraction in other two directions. So if we want to set up the relation, there is one coefficient which we define, that is known as the Poisson ratio. So you see these are all the coefficients which we define, which is which is always playing an important role to measure the strain in respective directions, like the three mutual directions. Also you see after setting those things, we calculated that actually if there is a combination of the load, like you see if there is a direct load is there, tensile load in x direction or y direction, then what will be the impact is there on that, means how we can calculate those strain component in the different parts of the material. Like you see if we cut the plane at an inclined plane, we are saying that the oblique plane, then what will be the strain components are there at the normal component or the shear strain component. So this kind of relations which we set up for when the axial loading is there directly, or when you see the combined loading is there, that means you see if you have the two mutually perpendicular axial loading is there, then what will be the relation, just like you see we have already set up in the stress part. And similarly you see the last part which we computed, that was you see that if we apply the load, the two mutually perpendicular loads are there, means the tensile stresses are there, sigma x and sigma y, in the same time the shear stress is there, sigma tau xy, then what will be the strain component at an inclined plane, that epsilon theta and the sigma gamma theta. Epsilon theta, which we are saying that there is a normal strain component in x and y direction, while gamma theta is the shear strain component, which we define separately. Then you see we got some of the relations based on those things, that actually how what will be the epsilon theta is there in terms of epsilon x, epsilon y or tau xy, or the gamma theta is there, that what exactly the relation is there, or we can say what the impact is there on those terms. So this kind of you see the relations which we set up in the previous lectures. And then you see we found that there is a symmetricity is there in between the stress component and the strain component. Like you see if you are talking about the stress, the similar you see the sigma theta or tau theta will give you the sigma theta. If you are talking about the normal stress component at the oblique plane, we found that it was nothing but the sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy by 2 sin 2 theta. So you see similarly we can also calculate the epsilon theta, the normal strain component under the effect of two mutually perpendicular stress with the shear stress, and that you see we can calculate that epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y by 2 cos of 2 theta plus gamma xy by 2 sin of 2 theta. And then you see again if you want to calculate the shear strain, then you see for symmetricity what we did is simply multiply by half. So gamma theta by half will give you the epsilon x minus epsilon y by 2 plus the square root of all that part epsilon x minus epsilon y whole square plus 4 times of gamma xy square divided by 2. Meaning is pretty simple, that you see we have an analytical part which we discussed in the stress component. Similar kind of impact is there on the analytical part of the strain component. So this is one solution when you see there is a combination of the stress components are there, we have you see the strains are there at individual point, and we can get you see the principal strains at principal planes. So, and also we set up the relation between the principal strains, like principal strains are there at where the shear stress component is not there, or when the maximum shear stresses are there, then what will be the angular relation, like 45 degrees there. In the last part of our previous lecture we discussed about those things. So, today you see, like in this lecture we are going to discuss about the graphical solution, as we discussed the same thing in like in the previous this for a stress component, that Mohr circle will give you, like the this geographical, or we can say the geometrical component, and to get all those things by measuring simple, like that what the radius is there, what the coordinates are there, you will get all the answers by which you generally you are calculating by the analytical way. So, you see here in this lecture now, here this Mohr strain circle is there, that is graphical solution. So, first to define those things, you see there are some technical terms which like this general definitions are there of those terms. So, we would like to first concentrate on those things, and then we will go for the Mohr strain circle. First of all, the principal strain, because you see the principal stresses are there, and we calculated the principal stresses just by keeping shear stress component 0. So, again you see we would like to calculate the principal strain by like that what exactly the impact is there of the two mutually perpendicular stresses with the shear stress component is. So, first of all, to get the strain at an oblique plane, because you see like we have all the components at the extreme ends of the particular cube. So, to get a strain on an oblique plane, two equations always you see like the epsilon theta as well as the gamma theta we need always to get those values within the strain components in the object, which are identical in form of the equations defining in the direct stress also on an any identical plane theta, because we are always keeping our oblique plane at an angle of theta. So, here you see these equations pretty like which we discussed recently, that the epsilon theta is nothing but equals to epsilon x plus epsilon y by 2, which is independent of the theta angle, plus the multiply of cos 2 theta, that is epsilon x minus epsilon y by 2, plus the gamma xy divided by 2 sin of 2 theta. So, you can get the direct normal strain component at the oblique plane if you know that two strain component, the mutually perpendicular epsilon x epsilon y with the tau xy and the gamma xy, which is the principal strain component, the shear strain component. Then you have the shear strain at the oblique plane, that is the principal strain, you see like we can say the gamma theta, which is half to make the symmetricity. So, half is nothing but equals to like epsilon x minus epsilon y by 2 into sin 2 theta plus minus sign, because like it is just trying to like make a contraction towards the other direction. So, we have this gamma xy divided by 2 cos of 2 theta. So, we have these two relations which is exactly similar like towards the stress component at the oblique plane. Since these equations for the stress and strain on oblique planes are identical, as I told you in form, so it is evident that Mohr stress circle construction can be based on equally well like to represent the strain condition using the horizontal axis for the linear strain. So, here you see like to make the Mohr circle, always we are taking the x axis just simply showing them the linear strain, or we can say the normal strain components, and the vertical axis always showing the shear strain. But since you see in the numerical problems we make it in the analytical solution we just make it half of there. So, our vertical axis will show the half of the shear strain. So, now you see now the basis, the abscissa. So, you can simply put the linear strain component towards the x axis, the half of the shear strain towards the y axis. And it should be noted that however the angles given by Mohr stress circle, this is the stress circle, refer to the direction of the planes on which the stresses act. So, you see here not the direction of the stresses themselves, means whatever the stress directions are there, the stresses we are not going to concern, but only we are checking that actually at what angle these stresses are acting. So, the similar things which we are going to discuss here also as far as the strain conditions are there, the direction of the stresses means, because you see we are not taking the individual angle of the stresses. So, the direction of the stresses therefore associated, you see if the basis of the direction of stresses, because they are coming from the direction of the force, associated stresses are always there for the normal, like that means you see at the 90 degree, because you see like whatever the angles they are making, there is a contraction and the extensions are there to the direction of the plane. So, always we are taking the normal to the direction of plane if the stresses are being associated with the strains. Since the angles are doubled in the Mohr stress circle, always we are taking irrespective of the 2 theta to theta s to theta p, whatever you see. So, always the Mohr stress circle is constructed based on the double of this angle. So, the in here also you see, like we are gonna just go for the similar kind of thing with the working relations of the rotation of the axis by 2 times of 90 degree. That means because it's a normal thing is there, so we have 180 degree which must be introduced in the strain circle. This is achieved by plotting positive shear stress strains vertical downwards on the strain circle construction. Always we need to achieve by simply like dropping the vertical on this particular strain construction. In the sign convention, like as we have already discussed that actually there are some sign conventions in these stresses part. So again similar kind of sign conventions are there in the strains, and here it is, you see the linear strains always as far as the normal strains strains are concerned, we are going to use if there is an extension. That means if there is an axial pulling is there, and if it is like going towards the extension kind of that, always will go for the positive because there is an extension and the strain is nothing but the change of length, that is the extension part, positive part divided by the original length. And if there is a compression, that means you see there is a reduction is there, so the overall impact, the change in length is the negative side, so minus means the change of length in terms of negative divided by the original length. So compression always gives you the negative part, extension always gives you the positive part. So correspondingly you see we need to take the sign convention as far as the linear strain is concerned. The shear of the strains are always taken positive when they increase the original right angle, because you see like if you want to measure the shear stress, that was nothing if you just remind that the slope of AOB minus slope of A dash O B dash means you see what exactly the like the change of the shear planes are there. Like if we have a common like the square is there, and if we are keeping those shear strains, always like the kind of distortion is there from their own place. So how you see distortions are taken place, and what exactly the final shape is, and correspondingly if like there is an increase is there in the original right angle of the unstrained element, we are always taken the shear strain positive. So again you see if you focus on the shear strain for Mohr stress, like a strain circle, the shear strain gamma xy, if it is positive, refer to x direction. The convention for strain are bit difficult for that, actually that exactly how they are rotating. The first subscript in this gamma xy is always you see like denotes the shear strain associated with the direction. That means you see if I am saying that gamma xy is there, so always you see shear strain is going towards the x direction, means the domain is the x direction, and the other one is told that actually what the force direction is there, and is what the extension is there. So example in gamma xy represent the shear strain in x direction, and gamma yx, if you just change the first subscript, it shows that the shear strain in the y direction. That means you see what exactly the point of like the influence is there in the shearing part. Always first subscript will give you that actually this is the direction of the strain. So if gamma xy is there, always it is going towards the x direction, like this distortion is there, and if gamma yx is there, the distortion is there towards the y direction. So this kind of you see like the notations are there, and that's why you see as we have discussed that actually these are the plane stress or plane strain forms. So these you see the combination of these two subscripts are there in that form. If under strain the line associated, you see whatever you see the line associated are there with the shear strain, the first subscript moves counterclockwise. Always you see like the CCW with respect to the other line, the shearing strain is said to be positive. That means you see like if the deformation, because as we told that gamma xy is there and it is moving towards the x direction. So if you are saying that due to that, if the line is associated with any of the like the strain part, and towards that if they are moving towards the anti-clockwise, means the counterclockwise direction, always we are taking the strain, shear strain, the deformation due to the shear stress is to be positive, and if it is moving towards the clockwise direction, then it should be taken as a negative part. The positive shear strain is always to be drawn on top of the epsilon, means the normal strain component, if the shear is shear gamma xy is to be given with respect to the this normal strain component. That means you see if we have the combined part, then how to draw like the shear strain with respect to the direct strain, or we can say the normal strain. This kind of like the relation is fruitful in that sense. Now come to like the real Mohr circle strain. So you see as we discussed the like the analytical part, that you see if you want to calculate the this normal strain component or the direct strain component at the theta, then it is nothing but equals to epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y by 2 cos of 2 theta plus gamma xy by 2 into sine of 2 theta. So this was the first equation which will give you the direct strain component at the oblique plane, and similarly we can get like the shear strain component at the oblique plane, that is nothing but equals to gamma theta by 2 is equals to minus of, because there is a reduction is there towards the shearing plane, so is equals to like epsilon x minus epsilon y by 2 sine of 2 theta minus gamma xy by 2 cos of 2 theta. So, you see these are the two key equations which will give you the two strain component at an oblique plane, which is one perpendicular to the plane, which is one is the parallel to the plane. And then you see what we are doing here, if we are writing again by simply like the first equation, we are simply like this is the independent of theta. If we are taking the towards the left direction, then what we have the epsilon theta minus minus this epsilon x plus epsilon y by 2 equals to this term, which is you see like dependent on the theta. So, we have one epsilon x minus epsilon y by 2 into cos of theta plus half gamma xy sine of 2 theta, means you see just a rearrangement of these things are there. And now if I am adding both of the term, you see the equation 3 and equation 2 by squaring, then what I have epsilon, this component, the epsilon theta minus epsilon x plus epsilon y by 2 whole square plus this the equation 2 the left part, that is gamma theta by 2 whole square. So, this square is equal to, now this is the term. So, you see if we are taking this term, then it is the whole square, you see epsilon x minus epsilon y by 2 cos of 2 theta plus half of gamma xy sine of 2 theta whole square plus this whole, you see of the equation 2 right side, you see it will be, since you see the whole square is there, so this sign will be positive and you can simply square of those terms. So, now you see if we expand these things by like a squaring term, then we can simply found that actually like there are some cos square theta terms, there are some sin square theta term, and there are you see like 2 sin theta cos theta terms are there. So, after like generalizing those things in both of the component of this equation, these two, what we will get here, we will get the epsilon theta minus epsilon x plus epsilon y by 2 whole square, this plus gamma theta by 2 whole square is equals to epsilon x plus epsilon y by 2 whole square plus gamma square xy by 2. That means you see like the pretty simple thing is that you see we can easily get those terms, which now all these terms if you see there is independent of theta, means if you are squaring those terms and you will find those things, then we will get the new terms, that is you see like epsilon 1 comma 2, that is nothing but equals to epsilon 1 plus, you see if you are taking those terms here, then what we will get here, we will get epsilon x plus epsilon y by 2 plus minus the square root of these things. What I did here, I simply like make the square terms of this and like put those things here. So, we have the two main strain terms, the strain terms are there, the new strain terms which are nothing but equals to, if I am talking about the epsilon 1, the new term, that is nothing but the epsilon x plus epsilon y by 2 plus square root of epsilon x minus epsilon y by 2 whole square plus gamma xy by 2 whole square. Okay. And if I am talking about the minus, then you see like this minus will come. And if you see here, if you are making those terms, then we have epsilon x, epsilon 1 plus epsilon 2, if you are just adding those terms, because you see only the difference in these two terms 1 comma 2 is just plus minus. So, if you are like keeping 1 and 2 and if you are adding those terms, then this square root terms will simply cancel out, because in first we are taking plus and in second we are taking minus. So, this will cancel out. So, we can say that epsilon x plus epsilon 1 plus epsilon 2 will give you the epsilon x plus epsilon y, because you see it is the sum of those terms. Or we can say that actually if we are like keeping those terms here, then we have epsilon 1 minus epsilon 2 by epsilon 1 minus epsilon 2 by 2 whole square like equals to epsilon 1 minus epsilon 2 whole square plus gamma square xy. That means you see if you are rearranging those terms just by the first equation and the second equation, we will get you see the final transformation of those things as epsilon theta just by this equation, this one. If we are keeping this one here, okay, so we have epsilon theta minus epsilon x plus epsilon 1 plus epsilon 2 by 2 whole square, because you see now we can replace this part here. So, epsilon 1 plus epsilon 2 by 2 square root of whole square plus gamma like theta whole square is equals to epsilon 1 minus epsilon 2 by 2 whole square. So, if like by these two equations, this equation and this equation, if you are manipulating those things, then we will get these equations. Or we can say if you want to plot those things, now it is pretty simple that actually there are at this particular level we have the two main information. One, that we have you see x square plus y square, this is nothing but you see x square plus y square equals to r square. So, we can say the radius of the circle is this r. So, r is nothing but the epsilon 1 minus epsilon 2 by 2. So, we have the radius, the fruitful information from that of the Mohs strain circle, and we have the center point, because you see x comma y is there. So, we can say like this the first thing is epsilon 1 plus epsilon 2 by 2. This is 1, you know, like because x minus theta is there, comma 0 in terms of the y. So you see there is no component with the this gamma theta, there is a component with the epsilon theta. So we can say this is the center point is there of those because x minus x1 plus y minus y1 whole square will give you the r square. So x1 comma y1 if the center distances are there or the coordinates of the center is there. So similar, you see, you know, like for the circle the equation, we can get the we can extract the information from that. So now we have two main important parameters to draw the most strange circle. One is the radius, that is nothing but equals to epsilon 1 minus epsilon 2 by 2, and we have the center coordinate, that is epsilon 1 plus epsilon 2 by 2 in the x coordinate and 0 for the y coordinate as far as the most strange circle is concerned. So you see a typical point P, if you want to measure, you see if you just you know, like remind that the principal strain the stress circle, then you see the similar terms are here. The principal point P is the central point of the circle given, you know, like by the normal strain and the half of the shear strain gamma xy associated with the particular plane. Always you see it is just giving by the oblique plane like theta or whatever. We note again that an angle subtended at the center of the Mohr circle always by connected two main points. Just you see, you know, two extreme points are there, and if you make those points, you see you can simply connect those angle which are subtended of the center of the Mohr circle by connecting two main points of the circle twice the physical angle of the measured which is measured in the material of the side. So that means you see always you need to take the 2 theta angle, that actually what exactly the connecting of the 2 points are there at the extreme corner of the strange circle. Since the transformation equations for the plane like the epsilon theta or the gamma theta in terms of the strain, you see plane strain are similar to those for the plane stress like epsilon, the sigma theta and tau theta, we can employ a similar form of the pictorial representation, and this is known as the Mahoney strain circle. Because you see, you know, like in Mahoney stress circle again the similar kind of equations came, and we discussed about that actually, you know, like on the x axis you can take the normal stress component, the y axis you can take the shear stress component similarly, and we get the similar equations at the oblique plane also as in terms of, you know, like the stresses. So here we can also plot the Mohr strain circle based on x axis simple the normal strain or the direct strain component, and on you know, like the y axis we can take half of the shear strain component. And the main difference between the Mohr stress and Mohr strain circle is the factor of half only, because you see, you know, like we need to keep, you know, like maintain the equilibrium side on the both of the side, so we are simply multiplying by half, so that this is the new term. So in terms of the stress component, you know, like the Mohr circle, we have only the sigma x was there, tau x was there, here we have the gamma xy by 2. So now you see, you know, like just whatever we discussed, it came here. You see we have on x axis the epsilon, we have on y axis that is the gamma by 2 plus and the minus. So now you see we have the center position. So center position coordinates pretty simple, you see epsilon 1 plus epsilon y by 2 comma 0, because there is no component on the y direction. So we have the center position, we have epsilon 1, epsilon 2 is there, this one epsilon 1 is there. So you see pretty simple, you can calculate the, these points, and you know also know the radius. Radius was nothing but equals to epsilon 1 plus epsilon 2 by 2. So you see, you know, like you can get this radius, and once you know these you know, like the y dash and this x dash these you know, like the coordinates, because pretty simple, you see you can get those things, the coordinates of these things, you need to plot those coordinates, make the straight, you know, like the diagonal, draw the circle. If you drop those things, then you will get the epsilon y and epsilon, you see, you know, like the x at those particular coordinates. So you have, you see all those things, and then you see you need to rotate by 2 theta p, where you see the principal planes are there. So this is my, you see, you know, like rotated, after rotation of those things we have this x dash and y dash, the strains are there associated with the this epsilon with the gamma xy by 2. So you have 2 theta, and then you see this is for the optimum plane and this is for the normal plane. So again you can calculate the C2 P coordinate by that. So point x dash and y dash simply represent the strain associated with these, you know, like the xy directions like that, in terms of the epsilon and minus gamma xy in terms of this below point, because x dash is there towards the downward direction. So we have the minus gamma xy by 2 as the coordinate. So coordinates of x dash and y dash we can simply calculate by the gamma this epsilon x minus gamma xy by 2. Here this is the x dash, because you see this is, you know, epsilon x is there, and this in terms of the this minus gamma xy by 2, or we can say as far as this y dash point is concerned, we have epsilon, you know, like the y, and plus since it is the positive direction, so we have positive this gamma xy by 2. So these, you see, you know, like we can simply calculate. So in x direction the strain produced the strain, whatever the strains are there by gamma x and minus tau xy exactly equals to epsilon x and minus gamma xy by 2. So, you see there is a symmetricity, only the half is the difference in the stress component, this shear stress and shear strain component, where in the y direction the strains are produced by this epsilon y and gamma xy, these are the positive one, and the similar terms are there by the sigma y and tau xy. So, as far as the y direction is concerned, it is pretty symmetricity is there, but as far as the x direction is concerned, we have, you see, only the half of the, like this minus sign is there, but they have the symmetric sign conventions. These coordinates are consistent with our sign convention, that means the positive shear stresses are being produced positive shear strain, and positive negative shear stresses are always producing the negative shear strains. That means, you see, if we are saying that this due to the shear stresses, it element is just going towards the clockwise direction, or there is an extension is there, or we can say, like the distortion is there towards the x direction is, like going in the anti-clockwise direction, we can say these are the positive shear stress and the positive shear strain correspondingly. And you see vice versa is there, always you see when the object is tending to move towards the counterclockwise direction due to the shear effect, or we can say this whatever the contraction, or we can say this distortion is there in the angle is towards, you see, like always going in the this clockwise direction, then we can say it is a negative shear strains or negative shear stresses are there. So, it is pretty, like the symmetricity is there in terms of the shear stresses and the shear strains. On the face AB, like in the previous figure, the tau xy is always positive, that is the strains are, you see, nothing but we can simply calculate the epsilon y comma plus gamma xy by 2. On the top of that, you see, if you simply notate that AB part, and as far as the BC, which is just below the diagonal part is there, you see, we can, like calculate the coordinates for BC also, that is the this tau xy is the negative, hence the stresses are the strains are also coming as the negative part, that is epsilon x is the x coordinate and the y coordinate is minus gamma xy by 2. So, you see, these are the key features which we, like simply got if the strain components are to be plotted. So, now come to the main feature. You see, this problem says that actually if we have the two mutually perpendicular stresses, like the gamma axis, you see these are there, and gamma y's are there, they are mutually perpendicular, gamma x towards x direction and this sigma axis towards x direction and sigma y in y direction. And if we have the tau xy, that is the shear strain component, and if it is tending to move towards, you see, like the clockwise direction. So, this is the basic element which we discussed lot in the stress component as well as the strain component also. We can simply, like just put the analogy here, that you see, if we have, like the LMN and the shear strain, you see there is no distortion, then we can simply get the O and this O and ML, means actually this particular element is pretty simple. But if you see the distortion is there, and if it is, you see, this L is simply moving towards L dash, or M is moving the M dash, or N is moving, you see, towards the N dash, that means there is a distortion towards that direction. Always the strain component, the shear strain components can be measured with the distortion in the angle, and then you see we will check it out that whether it is a positive or the negative direction. So, a typical point P, which you see on the top of that was there in the previous Mahoney strain circle, gives the normal strain and half of the shear strain associated with the particle plane. We must measure the angle from the x axis with the, because x axis is our reference axis, always we have taken as the required formula by epsilon this theta comma minus gamma theta of half of, because you see, this is simply measured on the oblique plane. So, half of minus half of gamma theta will be the y direction and epsilon theta is in the x direction, has been derived from the reference to x axis with the angle measuring in the counterclockwise direction, because you see in that actually we are always taking the strain component as in a positive way. So, now we want to construct the Mahoney strain circle based on whatever the information which we like discussed in the previous slide. So, in this we would like to locate the points of x dash and y dash. You see that what the exactly x dash y dash point will come of instead of this a b or bc which we discussed in that, and we also like we have done this kind of analysis or to draw the Mahoney circle in the stress circle also. So, the following the steps are there to draw the Mahoney strain circle. The first one, just we need to take the normal as well as the linear strain component on x axis, as I told you, whereas you see half of the shear strain component will come on the y axis. So, first you see take those points and then locate the points of x dash and y dash, and you see in the previous slide we simply found that actually what are the this influencing components are there to make the point of x dash and y dash. Once you make x dash y dash points, at these two places. Now join those x dash y dash point, and then you will have a diameter of the Mohr circle. And once you have the two extreme points of the diameter, simply draw the Mohr circle. So once you have the Mohr strain circle on this point, you simply get the center point, and the center point will give you that what exactly the locations are there of those other points. Once you do that part, then you see what you have a horizontal line on the strain part, that is nothing but the direct strain component, and you have this x dash y dash joining line. So now measure that angle. So measure the required parameter, whatever the parameters are there, and also the whatever the angles are there at those things. So here it is, you see all this particular thing. You have a epsilon part, the normal strain component on y this x direction. You have on y direction minus gamma y by 2 plus gamma by 2 in both plus minus axis of y, plus minus side of the y axis. And then you see you need to draw the x dash and y dash component. So you see this is x dash 1, this is y dash 1, because you have the coordinates in terms of the strain component. So once you plot those things, join this line. Once you join the line, now you have this the circle, and once you have the circle, you have the center point. Once you have the center point, you can simply get that what exactly the center point coordinates are there, epsilon 1 plus epsilon 2 y by 2. This is the coordinate is there. So once you have these things, then you can straightway plot from the origin. Then this is, you see, epsilon 2, this is exactly the epsilon 1, and the coordinate is epsilon 1 plus epsilon 2 y by 2 comma 0. These are the coordinates. Once you have these things, you see now you simply drop those vertical lines. Then you have on y dash side, you see you have the y coordinate, that is plus gamma y by 2. On x side you have minus gamma by 2. So you see both the things which you have the coordinates for this one, this epsilon x comma this plus, or I should say whatever you see, you can take any of these things, gamma by 2, and this is epsilon y comma gamma by 2. And then you see what the angles are there towards the major side, because we are taking always 2 theta. So we can say that this is the 2 theta angle is there. So these are the required parameters which you can easily measure if you simply draw the Mohr circle with the required whatever the given information is there. So now you see that actually how to draw the Mohr strain circle. If we have the different strain components are there with us, and we can simply get at the oblique plane also as well as the principal planes. So now you see the this example just gives you a clear cut feeling that actually if we have the numerical data, then how we can get all those things. So you see here, first of all, we have a certain point, the material is subjected to the following the state of strains, that is 400 times into 10 to the power minus 6 units, epsilon y is there 200 into 10 to the power minus 6 units, and gamma xy, that is 350 into 10 to the power minus 6 radians, because you see always gamma is means the shear strain is always coming in terms of radians, while you see there are the units because the epsilon these epsilon things are there, these are you see in the normal straight components we can straightaway measure in without any units are there. So determine the magnitudes of principal strains, that what exactly the principal strains are there, what is the direction of the principal strains, that means the 2 theta p at where the principal stresses the strains are occurring, and the strain on the axis at 30 degree clockwise to the x axis. Means you see if you cut the plane at 30 degree with the reference plane towards the clockwise direction, that means this is my location of the oblique plane. Now we would like to calculate that what will be the normal strain or the direct strain component and the shear strain. So this is the main the example is there. So now we would like to first draw those the Mohr strain circle based on these information. We have 2 strain component, normal strain component, and we have the shear strain component. So based on that, it's pretty easy for us to draw those things. If we can put the x dash y dash, make the diameter, draw the circle, get the value of center, get the value of this epsilon 1 and epsilon 2, and these are the principal stress, and then measure the 2 theta which will through which we can get the this angle where it is now, and then you see we can get by simply rotating the 30 degree towards the clockwise direction of the x axis. So you see all these things are pretty straight. Come to the solution. Now you see here, as I told you, first what we need to do, we have the x dash coordinates, we have the y dash coordinates. So you see simply plot the epsilon and gamma here, plot those these x and y on mutually perpendicular axis, plot those x dash and y dash, draw the line. Once you draw the line here, now you can make this particular circle. Once you have the circle, now since you see at the this extreme corner of the circle will give you the epsilon 2, this extreme corner will give you the epsilon 1. So, just measure those terms and you have the principal stresses. So, this is you see the required first answer, that what will be the principal strains. Then you see once you get those things, simply rotate, simply measure this angle, because you see like that what will be the this plane is there. So, now once you have the 2 theta 1, because this is the measured angle, that at what plane these strains are existing. So, now we have the 2 theta 1. So, we have the angle 1 now, and then you see they were asking that actually what will be the new like form of the axis if you like means what will be the new strain components at the direct as well as the shear strain. Simply rotate 30 degree to the clockwise direction to the x axis. So, now you see since it is 30, so we need to go with the 2 theta as we have discussed previously. So, 60 degree angle you need to make. So, now you see here the 60 degree angle, draw this drop. So, you see here this is the new coordinate will give you the new values of in the x as well as the y direction, and then you see we can say that this is my this epsilon theta, which is the this direct strain component at an oblique plane, and as well as you see you can get like the gamma theta just by keeping that part you see on the vertical direction. So, this vertical direction will give you this one. This vertical direction will give you the strain component in y direction. This on x axis, this projection will give you the strain in the x axis. So, you see you have both the component, the normal strain component and the shear strain component, by just dropping those projection from the x as well as the y direction. Meaning is very simple, you see we do not have to do anything, you see there is no numerical calculation, whatever the information is given, simply like put those information on this Mohr circle, draw that part, get the value of the like all those required items. So, you see here like once by drawing those things we need to measure that. So, you see you have epsilon 1, that is 5000 10 to the power minus 6 units, you have epsilon 2, that is 100 into 10 to the power minus 6 units, and you can simply measure the theta 1 and theta 2, because these two planes are always 90 degree to each other as we discussed in the previous lecture. So, once you have 30 degree and then you see add 90 degree. So, this is theta 1 and theta 2, these are the locations where these principal strains are acting mutually perpendicular. Then you see we have epsilon 30 degree, because you need to measure this kind of thing. So, you see simply put the horizontal projection. So, this is you have even this 200 into 10 to the power minus 6 units, or even you can also go for tau xy just by like putting the projection on the vertical slide. So, you can also measure that part and you can get all this kind of required information, which is you see like necessary and which can only be getting by measuring those drops here. So, the angles being measured in the counterclockwise direction from the direction of the epsilon x, that is what you see, it is like straight way we can get you see the positive values for these required items. So, you see these are the required parameters for which you see we do not have to calculate, straight way we can measure from the Mohr strain circle. So, this is done now. Now, there is a use of the strain gauge. There are like the gauges are there to measure the strain. So, although we cannot measure the stresses, because you see stresses are always inducing due to the application of the forces. So, we cannot measure that actually what the distortions are there or the deviations are within those object, and what are you see the kind of the resistances are being provided by the material against the application of force. So, it is not easy, or it is not even sometimes possible to measure directly the stresses. We can only calculate that part instead of measuring the stresses within the structural member, but we can measure the strain because there is a direct distortion or the deviation is there, or we can see the deformation is there in the object. So, we can simply measure those things, that what exactly the change of length, width or breadth are there in terms of the original one, or even the area, or even the this volume, and that is why you see like the volumetric strains are there or the normal strains are there. So, we can measure strains, from them you see the stresses can be computed as such. Even so, we can only measure the strain on the surface, just it. For an example, we can mark the point on the lines of the surface and measure the change in their spacing, whatever the angles are there, and in doing that we are of course only measuring just average strains or the regions concerned, and also in the view of very small changes in the dimension it is difficult to achieve the accuracy in the measurement. So, that is what you see like we need a perfect because as we know that while application of the load is there, whatever the deformation which are coming, it is very minimal. So, we cannot exactly go and simply measure that okay how much is there, sometimes it is in the microns only, then we have to be very careful just in choosing of the strain gauges, that what exactly the strain gauges are there for which this kind of measurement is suitable and we can get the accurate answer. So, in practice electrical strain gauges always provide the more accurate and convenient method of the measuring strains. So, you see here we have like the electrical strain gauge. So, what is there? It is simply a paper or the resin is there in which there are two segments. So, what we are doing here, this is simply like block the P of Q, you see this is the center line is there. So, if we apply any kind of the distortion or any kind of things are there, there is a change of the potential, means you see if there is a change of the potentiometer, that what exactly the potential change is there, and if we like this modify or amplification is there of that small change, it will give you the clear cut that actually okay, that what exactly the distortion or the deviation has happened in the element. So, electrical strain gauges are always based on that actually what exactly the change of the potential or the voltages are there within those elements. So, the gauge shown in above measure normal strain in the local plane of the surface in direction of PQ, whatever you see the PQ straight horizontal plane was there, which is parallel to the folds of a paper, like you see paper or resins are there. This strain is average value, always gives you an average value for a region like covered by the gauge rather than a particular point, you see, because what are the localized strain are there at a particular point. The strain gauge is not sensitive to the normal strain in the direction of perpendicular to the PQ. So, whatever you see the something is going on in the normal direction of PQ, it does not matter much here, because whatever the things are changing into parallel to those things, it is always concerned with that and it will straightway reflect those changes in their final reading. Or we can say like it simply respond there is no response you see to the shear strain. Therefore, in order to determine the state of strain at a particular small region of the surface, we usually need more than one strain gauges for measuring the normal strains as well as the shear strain component. To define a general two-dimensional state of strain, because you see always we prefer that actually wherever the application of load or the distortions or deformations are there, we found that there are both the component, the normal strain as well as the shear strain component are there. So, to define these general two-dimensional state of strain, we need to have three like pieces of the information. One, the epsilon x, that means the strain component in x direction, strain component in y direction, and the shear strain in xy, because all three kind of like the information is available whenever the kind of a load application is there. Refer to any convenient orthogonal coordinates in x and y direction. Okay. So, we therefore need to obtain measurement from these three at least three strain gauges, so that we can get all those required information in the respective direction in x, y and xy direction as well as the plane strain is concerned. These three gauges must be arranged at different orientation, because again you see like we need to keep those strain gauges in a perfect way, so that we can get exact deformation in a particular direction. So, three gauges, all three gauges must be arranged at a different orientation on the surfaces to like form a strain rosette. So, again we need to form a strain rosette to get all three respective directions, all three respective magnitudes of the strains in the respective directions. The typical example have been shown, you see in the next figure, where the gauges are arranged either at 45 degree or at 60 degree, which is perfect for the strain rosette. So, you see here in this diagram we have like the three rosette for x, for y and for this z, which is for gamma xy, means we can say that for axial strain this A and B is there, and for the shear strain we have the middle one at the 45, or we can say at 60 also this and this will give you the x and y, while the middle one will give you the shear strain component, or you can say this third diagram. So, a group of in above figure, a group of three gauges can be arranged, because in the triangular form you see you can form, because they are again forming in the 60 degree. So, this can be, even this figure can be replaced by this. So, three gauges can be arranged in particular fashion, which is known as the strain rosette. So, all three gauges to measure the respective strains in the respective directions, if they are arranging in the particular form, irrespective of the triangular form or any form you see right angle, they are known as the strain rosette, because the rosette is like mounted on the surface of the body just to measure that actually what exactly the deviation is there due to the application of load, where the material is in plane stress. Therefore, the transformation equation for the plane strain to calculate the stress is always in the various directions. Knowing the orientation you see in x, y or xy of three gauges forming a rosette together with the in plane normal strain, they always record all three respective state of strain at the region of the surface concerned to like whatever the regions are there, it can be easily measured and it can be found easily. Let us consider now a general case shown, you see now in the next figure, which has like 3 gauges. They are mounting at 1 2 3, where 3 gauges, 3 strain gauges numbered 1 2 3 exactly for the corresponding thing, and the whatever the angles are there, which like the distortion angle I should say here is theta 1, theta 2 and theta 3, which are like measured in the counterclockwise direction, refer to the direction of x axis. So here you see this is there. So we have the epsilon like this xyz is there, and we have you see whatever the distortion theta 1, theta 2 and theta 3 corresponding you see the strain gauges are there, epsilon theta 1, epsilon theta 2 and epsilon theta 3 with those 1 2 3 the gauges are there. Now you see like although the condition of whatever the strain gauges at a surface on which there are no shear or normal stress components are there. So these are the planes, rather we can say the plane strain component, we can still use the strain transformation equation, the epsilon theta and gamma theta, which we can still use like for the general transformation equation to express these 3 measured normal strains in terms of the strain component epsilon x, epsilon y, epsilon z, and this gamma xy refer to the x and y coordinates as shown in this particular figure. So what we can do here now, we have this epsilon theta 1, epsilon theta 2, epsilon theta 3, and as I told you, see we can straightway use those equations rather to compute rather to measure. So we have you see like epsilon x cos square theta 1, epsilon y sin square theta 1 and gamma xy sin theta 1 cos theta 1 will give you the epsilon theta 1. Similarly you see we can get epsilon theta 2 and epsilon theta 3 just by keeping those values in terms of theta 1, theta 2 and theta 3. So I mean to say you see that in if the theta 1 is there, then we have epsilon x, epsilon y and this gamma xy is there just to measure the strain component at theta 1. So similarly at theta 2 and theta 3, whatever the distortion is there due to epsilon x, epsilon y or gamma xy, it can be simply computed in terms of epsilon theta 2 or epsilon theta 3 when you see epsilon x, epsilon y and gamma xy distortions are there. So this is a set of 3 simultaneous linear algebraic equations you see in terms of both epsilon x, epsilon y and gamma xy linear like these 3 unknown. To solve these equations like is a pretty laborious part is there, because we have 3 unknown and we have the 3 equations. Again you see we need to solve with these equations with all the kind of manipulation, but with the computer it can be like easily as simple MATLAB programs are there, and we can simply keep those things and we can get the final answer using the, these things. The state of strain can also be determined easily at a point, and this is you see pretty informative informations are there, that rather once you know the theta 1, theta 2, theta 3, you can get like this whatever the strains are there at a particular value, which is known as the oblique plane strains. Let us consider now the optimum part, which we discussed, the strain rosette at 45 degree. Considering the 3 electric resistance strain gauges are there, can be arranged exactly in the corresponding direction x, y and xy direction, like in the middle one they are simply set up to the at 45 degree angles. Okay, so the gauge ABC simply measure this ABC are there, they are simply measuring the normal strain, this epsilon A, epsilon B and epsilon C with their respective directions. You see epsilon A, B, C, okay, OA, OB and OC, and once you see we can simply put those equations which we found that in the 3 algebraic equation, by keeping those things the 45 degree at that point, we have epsilon theta was nothing but the epsilon x cos square theta 1, epsilon y sin square theta 1 plus gamma xy sin theta 1 cos theta 1 was there. So by keeping that, theta 1 is exactly parallel to that one, so theta 1 is 0. So what we have, epsilon theta 1 is equals to epsilon A. So what we have, there is no angle, you are simply rotating 45 degree by theta 2 and theta 3, so only we have the 0 degree at first one, so we have epsilon theta 1 is epsilon A. Again you see we can simply epsilon theta 2 which is at 45 degree from the theta 1, so again epsilon theta 2 is nothing but epsilon x cos square theta 2 plus epsilon y sin square theta 2 plus gamma xy sin theta 2 and cos theta 2, keeping 45 degree, what we have epsilon theta 2 is nothing but equals to epsilon B. So what we have, you see epsilon B is nothing but equals to which we measured that actually the strain gauge B is there at the this point. Just by keeping 45, what we have epsilon B is equals to half of epsilon x plus half of epsilon y plus half of gamma xy, or we can say half of epsilon x plus epsilon y plus gamma xy by 2. So these you see the meaning is that we have straight relations that actually if you want to get those things, you can get the strain part, this shear strain part gamma xy by just you see if you know the b 2 times of just 2 times of multiply these 2 times here. So, 2 times of epsilon b minus epsilon x plus epsilon y. That means if you know the normal strain component at the middle portion at the 45 degree from the this one, you can easily get the shear strain component from that, or we can say that gamma xy is nothing but equals to twice of these terms. Now you see go back to the third one, which is exactly at the 90 degree of this one, the third C1. So now you see by keeping these theta 3 90, what we have epsilon theta 3 is equals to this EC, means epsilon C which is there. So epsilon C is equals to epsilon y. So we have epsilon A is equals to epsilon theta 1, epsilon C is equals to epsilon y. So we can easily get you see either A and like B from the x axis, and then you see what we have means epsilon A you see is epsilon x, epsilon C is epsilon y. So you see these are the normal strain component. The shear strain component is nothing but equals to twice of epsilon b minus of the summation epsilon A plus epsilon x plus epsilon y. So these three terms can be easily computed in for a strain rosette if it is like shifted at 45 degree angle. Thus you see like all these things, just by substituting all these things we have gamma xy is this. So this is the shear strain component, and the normal strain component is you see these terms are. Since the gauges A and C are aligned with x and y, so obviously they will give you the direct or normal strain component, while you see this middle one is settled with the like the shearing plane, so obviously it will give you the shear strain component. Thus you see all these can be easily determined from the strain gauges. Knowing these strain gauges, we can simply calculate the strain at in any direction like by means of the Mohr circle, or we can say from the transformation equations. Then you see come to the next portion, that is the 60 degree. So previous case was 45 degree. Now if you put the 60 degree rosette, then what we have epsilon x is epsilon A straightway. Similarly epsilon y, which is at the like just going beyond these things, if you make the triangle or if you just do this thing, then it is 1/3 of 2 times of epsilon b plus 2 times of epsilon c minus of epsilon A. So that means you see it is not exactly like vertical to the part A. So it is not, you see we can say that these are the normal strain component. They are, you see like since it is going certain beyond thing, so it has an impact of both the B as well as C, and this gamma xy is nothing but 2 by square root of 3, that is epsilon C minus epsilon B. So now you see in this lecture we discussed about that if we have the different strain component, then how to calculate like by using Mohr circle of this like the strains at the oblique plane, as well as if you want to measure the strain, because this is a measurable parameter, the strain. So you see which strain rosette will give you the perfect answer. So we need to arrange either at a 45 degree to get the optimum or the perfect value of the shear strain, or you see this 60 degree rosette is also usable in that sense. Okay, so in the next lecture now we are going to discuss about that, what exact applications are there in the real feature, that you see if we have a real bar, if we are applying the loads, then how we can exactly measure those strains, and once you measure the strains, then what exactly the relations are there in between like those stress and strain component for different types of material, that if we have like the ductile material, perfect elastic material, not perfectly elastic material, but there is some sort of distortions are there, then what exactly the relations are then between them, and what the properties are there of this material which will influence the relation between the stress and strains. Thank you.